Welcome to CP 329 UART lecture. Today we're going to cover how a UART works. We'll talk about both the wiring and the transmission protocol for UART. Also, I'm going to do an introduction to UART on the ATmega. So UART stands for Universal Asynchronous Receiver Transmitter. So asynchronous means no clock, and it's a receiver transmitter, meaning full duplex transfers, meaning you can transmit and receive at the same time. There's actually one pin for a transmit and one pin for a receive. There's a serial port on your computer if you have an older one that is a UART. Actually, nowadays they use a UART over USB a lot of times, and that's actually what we're doing with the Unos. And many microcontrollers have UART serial port. So in general, microcontroller with the UART is going to kind of look like this. Here's the CPU core, and here's the UART peripheral. There's our receive data register and a send data register, and bits get shifted in or shifted out of these registers. And there's usually some sort of controller status registers that allow you to manage the UART. So if you had two microcontrollers with receive and transmits, you connect the transmit to the other one's receive and vice versa. Do be aware there that you need to have the same ground here, otherwise these logic levels won't really mean anything to the other microcontroller. We can also connect a microcontroller to a personal computer in a very similar manner. And so basically this is what those COM ports are on your PC. Since there's no clock, the communication is actually paced, right? So the transmit and receive need to have what they call the same baud rate. Baud is really like symbols per second, but each symbol here is a bit, so it's really bits per second. And the baud period is the time that a bit is on the wire. So the smaller the period, the higher the baud rate. And it kind of looks like this. We idle high. And then the start bit is low by definition, and that's low for one baud period. And then we have the bits. So D0 here could be a 0 or 1, so it could be either high or low, similar with D1, D2, D3, D4, D5, D6, and D7. And then there's a stop bit, so it has to stay high for one baud period. And then you could start this again. You could have another start bit after this. So if we go through an example here, if we had this setup here, what's the value that's being transmitted? It's actually going to be, this D7 here is the most significant bit. So in hexadecimal, this is going to be 1110 is E, and then 0000 is 0 in hexadecimal, so this is E0. So UARTs are limited to small numbers of bits being transferred at the same time because the receiver and transmitter aren't synchronized. So basically, they have to know what baud rate each other is going to run at, and so, but they'll still have their own clocks, and they may not be perfectly synchronized. And so this graphic here is showing, okay, well maybe we're transmitting here and maybe receiving over here, and it may be happening a little bit differently. But as if the clocks aren't synchronized, the longer we go, the amount of error period starts to accumulate over time, and could actually spill into the next bit, and that could be a bad thing, right? So we won't be getting correct data essentially. So yeah, there's a cumulative error from timing variation between the transmitter and the receiver. So we keep UART transfers to a single byte at a time, or 8 bits. So UARTs can be configurable, number of configurations. We talked about baud rate. Could be 9600 bits per second, and it could be 100 k bits per second. And so usually most UARTs only operate in the 1 byte mode, or 8 bits. But there are some out there that will allow you to transfer more per start and stop bit. We can have the hardware generate parity bit, basically for error checking. And so it's, instead of 8 bits, it'll send 8 of the byte and then the parity bit. And we can also choose maybe the parity type. And we can also change the length of the stop bit. It could be 1, 1.5, or 2. Those common settings. There could be more. So if we're going to use a UART, we just set the configuration parameters. We enable a transmitter and receiver. And to transmit a word, we usually or transmit a byte, I guess. We would put it into a transmit data register, or if we're going to receive something, we're going to read it from the transmit data register. And there's usually some status bits. A transmit ready status bit will tell you when a byte has actually been shifted out of the transmit data register, and the receive data will actually flag will tell you when there's a byte has been fully transferred into the RX data register. So again, we talked about errors. The parity error could occur, indicating that parity doesn't match the value that you received, and so therefore there was a bit flip. So you can ask for maybe a retransmit. It could be a frame error if you don't detect the stop bit, or an overrun error when a new word has been received before the previous one has been read. And there could be noise errors where all the bits don't agree, essentially. So on the USART, on the ATmega, again, it's full duplex operation like every other UART, asynchronous or synchronous mode, so it actually has a clocked option as well. And it has its own baud rate generator, so you don't have to do anything special, you just have to configure it. Supports serial frames with 5, 6, 7, 8, or 9 data bits and 1 or 2 stop bits. Can do odd or even parity generation, and has automatic parity check hardware. It can detect data overruns and frame errors. It has some noise filtering capabilities that will filter out some of the noise problems. Can generate interrupts on when a transmit is complete, or a transmit data register is empty, or when your receive has been complete. It allows you to communicate to more than one value, so basically it has a good drive strength. And then it can do a double speed asynchronous communication modes, meaning that it can it can double up the speed of the baud rate. And so basically, here's their block diagram. You can see the control registers here, the UART control register, or status register A, status register C, status register C. Here's the transmit data register, and here's the receive register, UDRs they're called. There is all the parity and clock generation schemes here. Here are the actual pins. And here's the baud rate generator, and here's actually the clock that you could actually, if you want to run in synchronous mode. So I guess these are status registers and control registers. UART control and status register.